to the cloud. Okay, cool. So again, thanks for joining. I just put the notes document link again. Oops, I shared that directly with, okay. Welcome everyone. Sorry, I'm gonna start again. The notes document link is in the chat. Please click on that link, add your name to the roll call. Before we get started with our presentation on H5 Coro from JP and Rachel, I personally don't have any announcements, but if anybody else has any announcements, I wanted to open the floor. Feel free to raise your hand or just unmute yourself and share any announcements you have for the group. I don't know, Annie, if you had anything that you wanted to mention with this group as well in terms of ESIP announcements.
Just hopefully you saw, for all of you that are signed up for the ESIP update, that all the recordings from the July meeting are live on YouTube. So if there's something you'd like to rewatch or that you missed, I'll throw that YouTube channel in the chat.
Cool. Yeah, the ESIP summer meeting was really great. I highly recommend if you weren't able to attend this year, you can join us next year. It's going to be in Asheville, North Carolina. That's already been announced. I believe that it's going to be in Asheville, North Carolina next year. And this year, the ESIP Cloud Computing Cluster was fortunate enough to have 3 sessions where we did talks, tutorials, and a working session. The working session was super fun and productive. So I'd like to have those sort of like what we call the Cloud Native GeoJam. So I'd love to do that again next year and have even more time to work with people on cool Cloud Native geospatial stuff, like I got the chance to with JP and Rachel. Okay, cool. So unless there's any other announcements, I'm going to go ahead and give the floor to, I think, JP, you're up first, right?
Yes. Okay, yeah, well, thanks, Amy, for inviting us to share what we're doing. I'm excited to do so. Let me share my screen and see. Okay. So when I share my screen, I unfortunately can't see you guys. So could someone verbally tell me that they can see the slides?
Yep, I can see it.
Okay, great. Thank you. So yeah, so we're going to talk about H5 Coro. I'm going to talk about the kind of the history behind it and get us up to the present. And then Rachel's going to take it from there and talk about the future of H5 Coro and specifically extending it and using it to analyze mission data. So starting off, just an introduction to H5 Coro. So what is it? It stands for HDF5 Cloud Optimized Read-Only Package. It is a pure Python implementation of the HDF5 spec. And the goal has been, how fast can we read HDF5 files stored in S3? And I put in there, it's a growing subset of the spec. It is not the full specification. The specification is huge. We've tried to target the versions and the parts of the spec that are most used. And really, you know, we're using a certain set of data, specifically ASET2 data. And so it started out being very compatible with that. And it turns out there's a lot of other mission data that it's compatible with as well. How do you get it? We are open sourced under the BSD 3 clause license, and we're developing it openly on GitHub. So I put the link in right there. We look forward to people contributing, using it, writing issues, collaborating, all of the above. And then I always like to know who's paying for stuff. Sometimes I don't trust things if I don't know who's behind it. So what's behind H5 Coro is NASA's funded a collaboration between University of Washington and Goddard Space Flight Center to develop this web service called Slide Rule, and it's come out of that. So it's really being funded through NASA and with direction from University of Washington. So I wanted to structure my part of the talk just as a timeline, just to give you a history of how it all started, the challenges that we have faced and how we've overcome them and arrived at what we have today. So back in June 2020, this program called Slide Rule was funded by the ISAT-2 program. This is an eye chart of Slide Rule. I won't go into all the boxes that are there on the right. But just at a high level, our initial goal was to provide an on-demand web service to generate custom products using the ISAT2 data. And our initial target communities were snow depth and glacier researchers. Since then, we've expanded. The entire system was designed from the beginning to be cloud native. It runs in AWS, US West 2. And we use the ISAT2 data products that are stored in S3. Initially, we had to stage some of them, but then with the migration to the cloud, with NSIDC migrating the data to the cloud, now we just use the data sets managed by the NSIDC there. And from the beginning, we've worked extensively with the HDF group to use existing HDF tools to read the data in the cloud. So what were our options back then to read H5 data? So we needed to build this web service running in the cloud. We needed to be able to read the data, store it in the cloud. What were our options? Well, we could just, every time we needed to read an H5 file and process it, we could download it locally and open it up using the HDF5C library. I should have mentioned, all of our server-side code is written in C++. We could mount the S3 bucket as a file system using something like S3FS, and then just open it up like it was a local file system, a local file with the HDF5C library. The HDF5C library does have an S3 driver called ROS3, so we could have used that. The HDF group had actually starting maybe in the late, maybe 2018-ish, 2017-ish, has started development of something called HSDS, the Highly Scalable Data Service. It was, and it is, their cloud solution for HDF5 access. And there's a driver, they call them connectors, that you can plug into the HDF5 library to use the HSDS service. And lastly, we could have reformatted the data into a cloud optimized format. So these were the things available to us, and these were all the things that we explored. But as it turns out, those first 6 months, we found that really there were no good options to us. All of the options let me go back, like all of these options, they hit a roadblock somewhere or the other. So what were the issues with these approaches? Well, first, all the tooling, all the HDF5 tooling, all of it right now uses the HDF5C library underneath. So the ultimate performance and behavior of any of the tools pretty much always comes down to this library. And the library serializes all of the API calls. And what I mean by that is, if you were to have multiple threads running and each of the threads wanted to read a data set out of an HDF5 library, it would be perfectly safe for those threads to make calls into the HDF5C library, and those read calls concurrently. They could all just make those calls, and it would all be safe to do so at the same time. But inside the library, there's a mutex that locks it at a very high level. And so each of those calls, even though they're in parallel sent to the library, they're executed serially, one after the other. And that was a huge performance problem. The second thing is that all of the tools that we looked at, in one way or another, issue an enormous number of I/O operations. In a lot of cases, it was one I/O operation per chunk, which, if the chunk sizes are big, is okay, but the ISAT2 chunk sizes were very small, and so this proved to be a real big problem. And then lastly, as enticing as it is to have the data in a cloud optimized format, it wasn't in our budget to be able to reformat all of the data and rehost it. We did some analysis of what it would take and to process just for the ISAT2 data, which is not the only data sets that we're using, but just for the ISAT2 data, if we were looking at reprocessing all 500 terabyte-ish of data every 6 months when a new version came out, and develop and maintain that pipeline to do so, that cost would have exceeded our entire AWS budget. So just to translate and to host that reformatted data. So that really wasn't available to us. So I want to go in a little bit deeper in each of these problems, because kind of understanding the problems is really what sets the stage for understanding why we had to go the route we did with H5 Core. So the first problem, this serialization problem, where the API calls are one after the other. The thing to realize is that a single read of an object in S3 is typically, and I put that in parentheses because you can always change the parameters, but in general, it's much slower than a single read of a file stored on a local disk. So in most of the systems, certainly it's true for the systems that we're building, the EC2 instances that we're running in USFS 2, this is the case. But S3 can support thousands of simultaneous reads. I think when we started, it was hundreds, and now I think it's maybe like 2,500 to over 2,000 simultaneous reads of a single object before you start seeing performance degradation, which is astounding, right? So when you read it, if you were to read that object now simultaneously with many different reads, it becomes just as fast, and in some cases much faster than reading a local disk. So that's how you have to operate in the cloud. You have to be thinking in this sense of simultaneously reading a file, because that's how you get the performance. And so the mutex in the HDF5 library, which prevents that, is preventing the very thing that you need to do to get performance out of S3. Now, backing up a little bit, this is just a chart I put together just to stress why it's important that we need to parallelize out. Because when we first were going through this, some of the feedback that we got was, well, why don't you just run a bunch of different HDF5 processes, right? So each process can then access the data in parallel. And our answer is, we absolutely do that. We run as many processes as we can to access the data in parallel. We run as many machines as we can, but we can't scale to the level that we want to scale at if we're only scaling at the process and the machine level. In order to take full advantage of the resources available to us, we have to move down into lighter weight methods of parallelism, using things like callbacks, with async programming and threads for multi-threaded. So the way to think about this is, in our system in slide rule, it is not unreasonable to us to have, I don't know, 10,000 different reads happening all at the same time. If we have a processing request, not even a big processing request, we fan that out over all the nodes in our system. Those nodes fan it out to different processes. Those processes fan it out to different threads. And we try to hit S3 as massively parallel as we can. And that number can be in the thousands. Now, we can do that if we're managing a few dozen or 100 nodes in EC2. But if you're to say now every read from an S3 bucket has to be at the process level, and so now we're managing effectively Docker containers for every read. We're managing thousands or tens of thousands of Docker containers just to read the data, and that's not practical. We want to scale at the process level. We want to scale at the machine level, but we also want to take advantage of the lower levels of achieving parallelism, like threads and callbacks, to get that massive parallel read. And then another issue is this issue of all the I/O that the existing tools perform. So S3 is high latency, high throughput. So that means that when you initiate an I/O operation, it's very expensive to start. So every time you do a read from S3, the first byte that you get back is extremely expensive. And then every byte after that is extremely cheap. And so what you want to do is you want to have fewer larger reads over many small reads. So you pay that upfront cost fewer times, and you get the benefits of streaming back all the data very efficiently. Now, the existing tools were just not concerned about this because they were written for local file systems. And that just isn't the environment that you see in a local file system. And so we saw with data sets that consist of many small chunks, it explodes the number of TCP/IP socket connections. And then the per latency reads just dominate the overall performance. And we'll look at that a little bit more. And it's also true if you're traversing the file, looking at a lot of the metadata spread throughout the file, you see just a ton of I/O operations to accomplish that. So we did some, and I'm going to skip through some of these. They're in the charts, so you can go back to them. But we did some benchmarking, and we proved to ourselves what has been proved by a lot of other groups, that larger chunk sizes drastically reduce the amount of time it takes to read the file. So the initial chunk sizes in ISAT2 data was 80 kilobytes. When we bumped it up to 50 megabytes, you see these two lines highlighted. Runs that were taking 1,000 seconds went down to 60 seconds, right? Just drastic changes, all pointing to the fact that it's the number of chunks that was dominating performance. We dove into the file itself and saw where the code was taking all the time. The HDF5 library was taking all the time reading, and you can see we were plotting, how expensive each byte was to read depending on where it was in the file. And these outliers, these very expensive areas of the file to read, were all in the sections of the file that had massive numbers of chunks. So you can see this is a file in just one of its group. It had 11,000 some chunks. We had a read that there was 350,000 chunks that had to be read, and that was creating 350,000 TCP/IP socket connections to S3. And you do the math on the first byte latency, and you're spending hours just waiting for first bytes to come back. And this just, again, hammers that home. This is where we use CloudWatch to plot the first byte latency reading in S3, and you can see that we're seeing about 60 milliseconds for each of those requests to get the first byte back. Some of our own testing showed it a little bit better than 60. So, it depends on how you read it, how you measure it, but that's, 50, 60 milliseconds is what you can expect. So the last thing I want to say about this, though, is that you would think, well, then just make the chunk sizes bigger. Well, unfortunately, finding the quote unquote right chunk size is not the solution. It's not the long-term solution. And we found that to be the case as we pursued this further. So why is that? So there's many reasons why that just changing the chunk size is not the right answer. The first is that what is the optimal chunk size, right? So say we want to match the chunk size to how we read the data spatially. So if we're going to read sections of the data that are 10 kilometers, then we'll just make the chunk sizes about whatever it takes to store 10 kilometers of data. Well, the ISAT2 data is dynamic. So not 10 kilometers could be 1 megabyte if it's at night over the oceans, or 100 megabytes if it's over ice sheets during the day. So we can't just say we'll match a chunk size to a spatial extent. Say we'll match a chunk size to the size of the request. If someone's asking for a lot of data, make it a big chunk size. If little data, a small chunk size. Well, again, that's a user runtime decision that we don't have a priori knowledge of. In our system, we have people that are asking for little bits, and we have people that are asking for a lot, and we need the same source data set to serve both of their needs. We did play around with this idea of a break-even size, where we match the chunk size to how much it takes to read, how much data you can read in the amount of time it takes to get the first byte back. And if you do the math on that, then you're never more than a factor of 2 in how off you are from the optimal size. But the problem with that is that it requires an expected latency and an expected throughput. And even in our system today, we have different instance types that we can pay for that give very different variables here, right? We can get very high throughput or very low throughput depending on how much we're willing to pay. And not only that, but even if we fixed on a certain instance type, what's going to be right today is not going to be right tomorrow, right? What is performant in 2023 is not going to be performant in 2033, and we need these data sets to last. So the chunk size can be a Band-Aid. It can get us a little bit of the way there, but it's really not the ultimate solution. And then lastly, that third problem of rehosting. Again, I mentioned this. It's just we couldn't do it. We would love to have done it, but we couldn't do it. And the reason is that maintaining these massive data sets, it needs to be the responsibility of the data providers. And data services like us should not, and in our case, we could not bear the cost of reformatting and rehosting the data sets. Right? Not when these data sets are approaching, and some of them already are at petabyte scales. We just can't bear that cost. So what was our solution? Our solution was divide and conquer. Looking backwards, we still continue to work with the HDF group in improving the existing HDF5 tools. We're currently in a collaboration with them on a ROSES proposal to improve HSDS, and we work with them monthly to do so. And I've advocated quite a bit for the formation of a cloud-optimized subset of the HDF5 spec. The format is really, it's not that the format is necessarily bad for S3, it's the library. And so there could be a lot gained from making fully backward compatible subset of the HDF5 spec, just doing it in certain ways that were as fully compatible with the current tools to make it much more performant in the cloud. And some people are going down that path, but there's a lot more that could be done there. Looking forward, we advocate for NASA to use cloud-optimized formats for future data sets. Future missions, I just say it bluntly, future missions should not be using H5, not now. Unfortunately, there are future missions that haven't launched yet that are still baselining H5, and that's just, we don't think that's responsible. But in the present, we chose to develop a new cloud-optimized HDF5 library that attempted to solve all the problems that we saw with the existing tools to meet our needs today. So moving forward now, 6 months, flipping over to the new year, in January 2021, we started development of H5 Quorum. And then 4 months later, the first version of it got into production as an option. And so when we rewrote the library, we wrote the library from scratch to read the data in S3 as fast as possible, not having the problems that we saw in the existing tools. And these were the key features that we used to get the performance. So the first is that all the reads are truly concurrent. So multiple threads within the same application can issue these read requests, and those will get executed in parallel. If you've got multiple cores, they will truly be in parallel. If you only have one core, since you're spending most of your time waiting for IO, it's effectively the same thing. You're still getting very parallel access and performance. We use intelligent range gets to try to read the optimal number of dataset chunks in each read operation. You read too much and you're wasting bytes. You read too little and you have too many IO operations. There's a trade there. There's heuristics in the code. We're trying to do this. There's still a lot of work to get this number better. But we've seen that using intelligent range gets drastically reduces the number of HTTP requests to S3. And you're no longer being killed just managing TCP/IP connections. So that request I talked about before with like 350,000 connections, those numbers are coming down to like hundreds. Or thousands, a few thousands, and that's much more manageable. We use page reads to reduce the number of IO operations. So when we're traversing the file structure itself, and we have to read a 1 byte field, we never issue a S3 read to read 1 byte. We read a page, let's say it's 10 megabytes or whatever it is, and then we cache that, and any successive reads that need to read other fields in the internal structure of the file, well, they just check that cache first, and we drastically reduce the number of IO operations going out to S3. The system is serverless, so it naturally scales. It makes it a lot less complex, and there's no metadata repository needed. So we don't need to process and reprocess every 6 months as a new version comes out the whole ISAT2 data set. Instead, we kind of build the internal structure of the file on the fly, and we cache that. So as the competing threads are trying to read the data, they're traversing the internal structure of the file, and they're constantly storing what they encounter into a common metadata store. And then all the other threads, before they go out to S3 to read something about the file, they'll check that store and say, hey, have you hit this group before? Oh, you have. Where? Can you just tell me where it is? And I'll just skip, to the head of the line and go right there. And it turns out that, a lot of the same internal structure of the file are retraversed for every data set. And so you get a lot of speed up by doing that. I mean, I'd be happy to go into more detail of any of these bullet points afterwards. So just doing a quick benchmark. Again, benchmarks are highly subjective to the use case. This was our use case, and this is what made the difference for us. We saw when the best effort we had done before was with HSDS, and we were looking in the 3,000s to 9,000 seconds to do these, 2-hour plus runs to do some nominal processing runs. When we switched to H5 Core, we got those down to 2 minutes, just a order of magnitude speed up, just by parallelizing and reducing the number of S3 connections, S3 range gets really. So it really turned the corner for us. So with that, by the end of that year, we had put together the first Python bindings for it, and we dropped our support for the existing tools by the end of that year, and H5 Core became the stable and only supported option in slide rule for accessing the H3 data. So that's where we've been now for about the past year and a half, 2 years. It's our sole method of access. It continues to perform well in production. We still find bugs, though that number has tailed off in the past year. Though we do still encounter them from time to time. We're using PyBind 11 for Python bindings, and there have been a couple external groups that have used H5 Core in Python programs. We're reading a handful of data sets, not just like 2 data sets, and it's shown itself to be compatible. It's shown itself to be compatible with some NetCDF files. But there are still some significant areas that need development. I'm going to list them right here. We do not yet support multi-dimensional data sets, only time series, and that's huge. That's the thing that we're most immediately working on. And then there's some more obtuse things like variable length data types and global heap, and some of the internal message types are not supported. Those things are less likely to be a problem, but are still needed to round out the support of the spec. But it really didn't stop there. And the reason it didn't stop there was that the Python bindings were a pain. In order to use the Python bindings, you had to build the C++ code. In order to build the C++ code, you had to set up the development environment that was needed to build slide rule, because it was built as a part of slide rule. And this is not a trivial thing to do. And so great care had to be taken to build the code for all the different environments. So if you were building on ARM, there were different issues than if you were building on x86. If you're using Conda as your package manager, there's different issues than if you were using your OS package manager. And all the different combinations of it meant that it was just extremely difficult to maintain for even a small number of people that were using it, and it was taking a lot of time for us to keep it working with the latest updates on all the packages and architectures. So we had 2 options: either rip it out of slide rule and make it standalone and have as few dependencies as possible, or create a pure Python implementation, and we went with the latter. So this past summer, we developed a pure Python implementation of H5 Coro. And that's kind of where we are right now. We have a system that's in fully matching the functionality of the C++ version. But we're still actively developing. We're working through some of the user interface issues right now. Specifically with Rachel coming on and looking at these things. So just at a high level, users can instantiate an H5 Core Python object for every H5 file in S3. And then there are class methods that can be used to read the multiple data sets from the file at the same time. And the data is returned back as a promise that can be later waited on. Again, I'll mention that, benchmarks are very subjective, but for our use case, We subset ATL03 granules. That is like one of our main things that we have to do in slide rule. And so just looking at the performance of that using this Python implementation of H5 Coro, if we use S3FS, it takes about 17 seconds to do so. If we use slide rule, it takes a little over 1.5 seconds. The Python version is a little under 3.5 seconds. So it's not quite at the performance of the C++ version, but it's certainly much better than using something like S3FS. Now, and then just for completeness, reading it locally, since you're just reading a small portion of one file, it's super fast with H5Py. And H5 Core reading it locally, again, is also pretty fast, but it wasn't designed for local file systems, so it's not really the same speed up that you might expect. But anyway, it was enough to say that there is promise here, and so we've decided to continue with it. And with that, I think I will hand things over to Rachel.
Okay, thanks, JP. Sec here. Okay. All right, so as JP mentioned, I'm much newer to this project, but came in thinking specifically about the Python aspect of the project. The theme of this, I'll be brief, but the theme of this piece is definitely data structure. Like, what is the Pythonic data structure that we want to be thinking about? And so I'll go through first a couple of the challenges specific to ISAT2, and then talk about some of the user experience things that we've been thinking about, and then kind of end on something that we're trying to do to improve the experience here. So just JP's already done some orienting to ISAT2, but I just wanted to do it one more time because I know we have a variety of people who are familiar with that data product or not. This is a picture of or a visualization of what some of that data looks like. This ISAT2 data, it's a LiDAR data system, and it and this particular product that we've been talking about, or I'll be talking about, ATL03 it's called. They're geolocated photons. So we're actually looking at where is a particular photon measurement found in space. So this visualization came from Jonathan Markle and is part of the ISAT2 Hack Week. Now, getting to the part about the ISAT specific data challenges of the ISAT2 data set, I want to point out that it is this HDF as folks might be aware, is set up in sort of a group data set structure. So it's very much like a folder and files inside of those folders. And there's a lot of data sets within this thing, close to 1,000 in this particular file, spread out over 150 groups. So it's super nested, the way this data set is set up, sometimes 2 to 3 levels of nesting. The other thing I'll point out, and this JP has spoken to this, is this notion that, well, we have, this particular file I'm using as a random example is maybe 7-ish megabytes of metadata. It's stored in 4 kilobyte chunks. And so that bit about accessing just the metadata or the structure is rather complicated, and accessing the structure is something that, because of those 4 kilobyte chunks, can also be challenging. So an example of looking at this is a snippet of code, which would, for example, when you open the data, you might want to, for example, figure out what are the groups and in which variables, what are the variables and in which groups are they located? Get your internal sense as a user of what am I looking at inside of this file? And when you run this on a local file using H5Py, it runs in about 0.5 seconds. So not something that is necessarily going to slow you down. When you run that same bit of code on an S3 file, it takes on the order of about 2 minutes. So just, I know we have these discussions, we're often talking about reading the data, where are the photons in this case. But in the case of these ISAT2 data sets, even determining the structure of the file, JP mentioned that internal caching, or that the traversing of the file and caching the structure becomes something that it does contribute significantly to the performance here. So in terms of approaching an ISAT2 data set, traversing the file, just figuring out what's in it, does tend to become your first major data read challenge. Other things that come up when you're using H5 Coro, or that we've been thinking about as we've been developing the Python version, are things such as the fact that because of the multi-threading, the code is an async code. So what happens is when you run a read data set call, it returns a future. Which makes a lot of sense from the multi-threaded perspective, but can be confusing in that when you run the same thing twice, you get something back different in each of those 2 times. The other piece that we've kind of grappled with is back on this theme of data structures is whether or not to maintain the really highly nested structure of this data or not. So we've gone back and forth between flattening it versus being in more of that tree structure. So these are the kinds of things that we've been thinking about in terms of where the Python version of H5 Coro might land. One of the things that I wanted so we came up with one potential way of approaching some of these. And to kind of contextualize why we chose that, I wanted to kind of remember or sort of think about the way that we think about H5 Coro in the broader ecosystem. So in terms of data access broadly, of a user using science data, I sort of think of it as there being multiple layers that kind of sit on top of each other in this. So at the very bottom, we might have a data spec for something like an HDF file. And on top of that, we have our IO libraries like netcdf or Rasterio, which do the actual reading of the data. They're sort of implementations of the spec, and they return something like a NumPy array. So we're kind of pretty close to the core numbers. And on top of that, we have sitting things like pandas or xarray, and those are what I would argue that what a big benefit of what those are doing is they're building Pythonic abstractions of the lower level data format. And so H5 Coro we see is sitting in this middle in the IO library piece. And so in order to try to connect, think about like what a user might want in terms of a structure. We're trying not to get too stuck on just what H5 Coro could return, but consider the fact that really a user probably is going to want to traverse this full tree. And so what we take in a pass at is to come up with a way to make an xarray backend for the H5 Coro engine. So this is an example of what a user reading code would look like in this. And so what we have happening here is using the Earth Access library to authenticate, putting together an S3 URL, logging in, and then an open dataset call to xarray. You give it the path, you specify your engine as H5 Coro. Where it's at right now, you specify a group, which is sort of necessary from the sense of what kind of data structure an xarray dataset can handle. It can't do all those level of nesting, so you really have to give it a specific group. And you're able to add additional parameters. So we can have our authentication parameter, for example, here. This was something that one of the biggest benefits that we were excited about in this potential solution was that higher level libraries, in the case of ICET2 like IcePix, can pretty easily switch into using H5 Coro. They don't have to actually start running H5 Coro calls, but can continue to use xarray in the way that the IcePix library currently does. The drawbacks is that perhaps not all of the data would fit into an xarray structure. The ICET2 data even is an example of that. The fact that you're required to have, we need to have that group argument, or to get at a lower level, you'd have to have that group argument. There's definitely, it's still in development. This is a really early thing. We've just started working on this. And so things that we're thinking about, kind of open questions that I think are rather interesting is considering how would a multi-threaded parallelism approach like H5 Coro sit with a process level parallelism approach on more the Dask level. And also would something like, what are the other structures available? Would data tree be something that would, the data tree library for xarray be something that could support those higher levels of nesting for us? So I'll end on one more idea here, and which is kind of pertinent in this sort of the LiDAR data, and perhaps more broadly, and that's this idea of what is the ideal Python data structure. I've mentioned IcePix here, which is a very, very common Python package for accessing ICET2 data, and IcePix tends to use xarray for its data structure. Slide rule that JP has been talking about tends to use pandas for accessing, for holding the Pythonic data structures. And so there's this kind of question of what is the better data structure for that. If anyone who's taken a GIS class, you might have had in that first day, right? There's this notion of like, there are two geospatial data formats. You have your rasters and you have your vectors. And I feel like if we go back to the stack, we kind of have a stack of tools that goes right up the pyramid for this kind of raster stack. And there's sort of a tool for the tabular data stack. And I'm curious about where LiDAR data will kind of sit in this. Will LiDAR data sort of fit into one of these tabular raster, or will there be kind of additional Python data structures that emerge to kind of meet that? So for now, H5 Coro sits at the IO level, and so we'll continue to focus there. But I think these questions of data structure are things that we kind of have in the back of our mind as we think about H5 Coro to consider how the whole arc of a user interacting with H5 Coro would. So with that, I'll say it's coming along, but there's more to come. We're excited to chat more about it and hear questions.
Awesome. Super interesting stuff. I know I have some questions. I'm sure other people have questions. I see one from Martin in the chat. Martin, did you want to go ahead and read your question out loud?
Yes, I am the author of Kachunk and S3FS, so I have the stuff we can talk about, but I had a couple of small clarification questions just to kick things off. The first is that when you open a file from a new process, you haven't seen it before, you have to pass the metadata, right? That's something you have to do for each file in each new process. Is that right?
Yeah. Yeah. If you were to open a file in a new process in the Python, you would need to rebuild that metadata. Yep.
Okay, and I just had one clarification. You were comparing using different things, and one of them was S3FS. So I was wondering how you were calling S3FS in that particular table. This was using H5Py or
Yes,
something else?
It was using H5Py.
Okay, so S3FS with serial calls in that case.
However, H5Py does it.
Yeah, mutex, right. You specified mutex, didn't you? Yeah, okay. Thank you. So I have plenty of stuff that I could say about Kachunk and things, but maybe other people want to comment before I do that.
Nice. Thanks, Martin. Yeah, I definitely think we could, return to that line of discussion. But Alexander, did you want to go ahead next?
Yeah, thanks. So hi, JP.
Hey, how's it going?
So I have a question, two questions actually. First one, when you talked about data set chunk sizes and not being, not having any recommendation whatsoever. So what's your choice? Or what do you think should be a data set chunk size? Because people will want to chunk, so they have to choose a chunk size.
Yeah, I think that ideally you want to balance out the compressibility of the data, and so you want to balance the amount of overhead of how well it compresses, and that should be your gauge, and you make it as small as possible with that in mind, that you don't want to have the overhead of the compression drive anything. When you do that, you then want to have the chunks arranged serially in the file. And so that way, if we have like chunked metadata, or if we have HSDS metadata, or what is it, DRR plus plus, or
DMR
whatever
plus plus.
DMR any of those that give you the metadata for the chunks, then you can intelligently combine chunks based on your application. And I can make them of any size I want, and I can tune it at runtime. If you make them too big, you lose your ability to do that. Now you can't make them too small, because ultimately you're compressing those chunks, and you need to get good compression ratios out of it. So that's my down in the weeds recommendation. But it requires there to be metadata that points into a single object where those chunks are sequentially stored, I should say.
No, yeah, but I was saying, like, you have to tell them some range of bytes when you give people some kind of advice. That's what I'm saying. And I agree with you. Is it 100 megabytes per chunk, or is it 1 megabyte per chunk? That's the question. What range people target, and also, from your talk, basically, you assume that all the computing will go into the cloud, and those files will never be downloaded or used in any other way outside of a cloud environment. Because if you go for 50 megabytes chunks and things, you're now talking about machinery that can effectively paralyze processing all those chunks.
Yeah. I would tend for the smaller chunk sizes, like whatever makes sense with the compression. It's probably single-digit megabytes right now. But that requires analysis on the compression. It requires that the data be sequentially stored. Not all H5 files have the chunks serially stored. And it has to be if you're going to do that. So it's kind of a bigger question than just the chunk size. And at that point, the chunk size becomes a lot less important. And you really, it's just a tooling around it.
And my second question is, have you actually used cloud optimized ISAT2 file? I've been talking about cloud optimizing HDF5 files for 2 eCIPs now. And there is actually a session now that someone mentioned, the YouTube videos are out. There's a session where I talked about cloud optimizing HDF5 files.
We should do that.
So,
yeah, I fully agree.
Because you could basically enable, even with ROS3 VFD, that comes with the library, which is absolutely not the thing for cloud native computing, to get essentially everything in the file at very close to the speed that you would get the same information when that file is on the file system. So I think in some ways, although now I know that H5 Core started way before that was known, I think that would help people not having to develop a new HDF5 format reader. I think that right now with those kind of files, you get from the library all the information that you are now trying to get by writing your own reader.
Yeah, it doesn't get you all the way there. We can. So my experience has been that for when Rachel was talking about traversing the file, having all the metadata stored up front matters. But you still have tooling that's accessing the data potentially at the per chunk level or a fixed block size. And so I still believe there's work to be done, though I fully agree that it's the right direction to go, that we need to have a very tight spec on a cloud optimized HDF5 specification, including some of the things that are being done now, but I think it has to go further.
Oh yeah, just to clarify, I didn't say that you need the library to read the data. I'm just telling you, use the library to get the file metadata. In other words, where things are in the file and what are they.
Yeah.
And then after that, you can plug in that information into your machinery.
Yes.
That's what I was referring to.
Yeah, it would be, yes. I think, I know that there's been a talk of future versions of ISAT2 going that way because it preserves all the tooling. I think it's a win-win to do that.
All right, that's all. I'm sorry that took some longer. I apologize for that.
Nice. I think Rich had his hand up next.
Yeah. I'm probably going to ask with a question like that Martin was going to ask if he would have kept going, but I joined a little bit late, but I didn't hear anything about Kerchunk. You might have mentioned that at the beginning, but I guess I'm curious, a lot of those same issues that you had, with inefficiency of reading HDF5 files are, also addressed by Kerchunk, right? Like not rewriting the data, reading the metadata at once, reading async in parallel, yada, yada. Have you guys done some comparisons, or do you have thoughts about, the differences between taking the Kerchunk approach versus the H5 Coro approach?
I think Amy and Rachel could speak to some of the performance testing that they've done, and it seems to be about the same with H5 Coro and Kerchunk. I would tell you that in our group in University of Washington and Goddard on slide rule, we are pro Kerchunk. We think that some of the historical data sets should be Kerchunked. And I've said in other forums that as soon as NASA wants to Kerchunk the ISAT2 data, that month, H5 Core will support it. We just can't do it. We can't reprocess petabytes of data for all the different data sets, JEDI and ISAT2 and other, the other missions that we're supporting. We can't reprocess every 6 months when the new version comes out.
You mean creating the Kerchunk metadata?
Yeah, we just don't have the budget for it. And NASA should do it, right?
Yeah.
I think, yeah.
Yeah, I think, the attraction, I guess, of doing some of these, if there were things that you had found, H5 Core that still needed to be done in Kerchunk, that would be kind of cool, right? Because the nice thing about Kerchunk, of course, is that it can work with other types of file formats as well. And maybe do the multidimensional stuff and other things that you're still, okay. Thank you.
I did think it was pretty interesting when we were in, other folks in the call could speak to this, but I believe it was when the kerchunking was happening of those files, it took something like 20 something minutes to kerchunk a single file, with the way that the metadata was spread around. So
I would strongly suggest using H5 Kuro as a way of doing that kerchunking. That would be an interesting thing.
I think we talked about that, didn't we, Rachel?
Yeah, I think that did come up.
Especially the small metadata pieces. Kerchunk doesn't do anything smart about fetching those. It's only when you're fetching the actual data that it consolidates reads. So the typical caching strategy for a single HDF5 file for getting the references in the first place is just to keep the first block, because quite a lot of the metadata is in the first block, even if you haven't done anything special. And in the best case, all of the metadata is in the first block, but that doesn't seem to happen as often as it should.
That's what I'm saying. Cloud optimized HDF file, that 20 minutes with the cloud optimized iset file will go to 1 second. I tried. So that's what I'm saying.
Yeah, well, the Kerchunk targets archival files that cannot be rewritten. So it has to
I know. I mean, that's like, that's the past is the problem. We hope that future will be better.
We could have I gave a talk about Kerchunk to ESIP about a year ago. So that recording should be around. And yeah, we can pass you the link. It's a different way of doing something similar.
There's a nice recent improvement in Kerchunk for very large, when the reference files get very, very big, as they do when the chunks are small, that storing the data in Parquet, which is a pretty cool development that somebody, I think at NASA, contributed, right?
Mm-hmm.
Yeah, that was organized by Shell, that development. And there is one example, this is still in PR, on Earth Access, of making Kerchunk references on the fly, which I think, as it's programmed at the moment, only lasts as long as your Python session. So you lose them at the end of that. But it's another interesting way to do it.
Interesting. Yeah, I'm trying to think. So it would be an interesting experiment, is what I'm hearing, to also speed up Kerchunk with H5 Kuro, but that wouldn't work out of the box, right? We need to build like an H5 Kuro backend for the Kerchunk library as well.
It would probably work out of the box. I'm not sure. And a good thing about that is that the end user wouldn't need it. The end user would just take the references and they don't care how they were made.
Right, totally. Yeah, absolutely. Yeah, I was just looking back. It did look like Kerchunk performed as well as H5 Kuro, but if we had H5 Kuro as a backend for Xarray, could work even faster, right, Rachel?
Right now, so others should jump in. It's sort of the Kerchunk does. I mean, Kerchunk reads ZAR, right? Kerchunk,
right.
Like once creates a ZAR looking thing. Others should jump in. They know much better than I am. So Xarray would then be reading the ZAR if it was reading the Kerchunked version effectively.
Yeah, when it's scanning files, it uses H5Py directly. So I don't know. I don't know enough about Kuro to know how you can plug that in, but it must be possible.
Yeah, I think so. Okay, that makes sense. Thanks, Rachel.
Well, also,
oh, go ahead.
Well, I was just going to say also, I don't know if these data, do they only exist on the cloud, or do they exist on some system somewhere where the references could be generated, by Kerchunk locally or something, which would be much faster as well.
That I don't know. I think they're just on the cloud now. Yeah, anybody else have questions for Rachel or JP or anybody else on the call?
There was a question by Rob Casey.
Oh, from Rob. Yeah, thank you.
See, with intelligent range sketch, does this mean that arbitrary large number of accesses are collected into smaller chunk reads? I think that's it. Yeah. So what I meant by the intelligent range gets is that you're reading the initial way to read was just here's a chunk and there's a range get read to read that. So the range get is just the read from this byte to this byte. And really, if you know that you're reading 1,000 chunks and you know all of those chunks are next to each other, well, now there's this trade. So you can read all 1,000 in one read, and that reduces context switch and thread overhead on your server side. Or you can try to read all 1,000 of them in 1,000 concurrent reads, which reduces how long you're waiting for I/O, but increases the CPU load on your server. And there's somewhere in the middle that's optimal. And it turns, the two extremes are horrendous. You don't want to read if you were reading 7 gigabytes, you wouldn't want to read 7 gigabytes worth of chunks in one read. And if you're reading 350,000 chunks, you don't want to read 350,000 of them concurrently. And so we've tried to do some middle of the ground heuristics to optimize that. And I can tell you there's a lot to be done there. We kind of got it good enough. And, but there's more work to be done there.
Yeah, it's a very sensible strategy. And I was just kind of curious on your read on that. Thanks.
Yeah.
Okay, perfect.
I have to go.
Yeah, we're at time. So if people need to head out, that is obviously understandable. And I don't want to take any more of JP and Rachel's time. Thank you so much for presenting today and putting that together. Super interesting, and I think has some applications across the approach to cloud optimized across the library sort of spectrum. So thanks for doing that.
Thank you.
Yeah, feel free to drop off. I was going to stay on for a few extra minutes if anybody is interested in talking about either takeaways from the summer meeting or talk about topics and activities that you want to see, you want to have be a part of the cloud computing cluster. I did